In Digital 1 of the You Can Do series, you learned how to convert from binary to decimal and from decimal to binary. You also learned that the binary system is the system most commonly used in digital circuits due to its simplicity in having only two states of energy. It is either on or it's off. It is very easy to make mistakes in addresses and information when using binary notation due to the large number of digits required to express a given quantity. Therefore, some computer systems make use of a notation called octal notation. In octal notation, a group of 3 bits is represented by a single digit. The octal system contains 8 digits, 0 through 7. As you can see, each digit in the 3-bit binary group carries a weight of 1, 2, or 4. Since each 3-bit binary group has a base of 8, they will increase from right to left by the power of 8. Thus, each group of 3 increases in value by a factor of 8 times the value of the previous group. Converting binary digits into octal notation is a very simple process. For example, to convert this 12-bit binary number into octal notation, first we must divide the binary bits into groups of 3, starting from the right. Next, we assign the weight values to each of the 3-bit groups. Then we add the values of each weight, which contains a 1 for each of the 3-bit groups. At this point, we see the binary number 100011111001 converts to 4371 in octal notation. Now suppose we had only an 8-bit binary group of digits. As you will see, the conversion process is the same regardless of the number of binary bits. First, we must divide the digits into groups of 3, starting from the right. Then we assign weight values to the binary bit groups. As you notice, the most significant bit group only contains 2 digits. Basically, we could say this group does not contain a 4, so we will place a 0 below this weight factor. Next, we simply add the values of each weight, which contains a 1, for each of the 3-bit groups. This shows us that the binary number 100111101 is equal to 235 in octal notation. Another commonly used notation group of digits is called hexadecimal. Most of today's commercial and personal computers use the hexadecimal notation system. In hexadecimal notation, a group of 4 bits is represented by a digit or letter taken from the hexadecimal characters shown in this table. As you can see, the hexadecimal system contains 16 characters, which are digits 0 through 9 and letters A through F. To write a binary number in hexadecimal notation, you must first divide the binary number into groups of 4 bits, or nibbles. Each nibble can then be represented by a single hexadecimal character. Next, we assign weight values for each of the 4-bit groups. Then we simply add all the weight values which contain a 1 in each 4-bit group and assign the appropriate hexadecimal character. As you can see, the binary notation 110100111010 may be represented by the hexadecimal notation D3A. As you saw earlier, the hexadecimal characters 0 through 9 correlate directly with the binary equivalents using the binary weights 8, 4, 2, and 1. But when the binary weight totals equal 10 or more, then the hexadecimal characters A through F are used. A represents 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. So far, you have seen how to convert from binary to octal and from binary to hexadecimal. At this point, we are going to learn how to convert from decimal to octal and then from octal to hexadecimal. Let's begin with the decimal number 612. Since the octal uses a base of 8, we must divide the decimal number 612 by 8. This equals 76 with a remainder of 4. The remainder will become the least significant bit of the octal notation number. Next, we divide 76 by 8. We see that 8 will go into 76 9 times with a remainder of 4. Therefore, 4 becomes the next most significant bit. At this point, we divide 9 by 8. 8 goes into 9 one time with a remainder of 1. The remainder of 1 becomes our next most significant bit. Since 8 will not divide into 1, it becomes the most significant bit. As you can see, the decimal number 612 may be represented in octal notation as 1144. To convert octal number 1144 into hexadecimal notation, it is easiest to first convert the octal number into binary notation, remembering that each octal digit is equal to 3 binary bits. At this point, we divide binary numbers 0010, 0110, 0100 into 4-bit groups or nibbles. Next, we assign weight values to the 4-bit groups. Then we convert the binary nibbles into hexadecimal characters. So far, we have seen that the decimal number 612 can be represented in octal notation as 1144, and in hexadecimal notation as 264, and in binary notation as 1001, 100, 100. If our conversions are all correct, then the binary notation 100, 110, 0100 should convert back into 612 decimal. To this point, you have seen how numbers are represented using positional notation and a binary base. You have also seen that large numbers require many binary digits to express the numerical value. So in the interest of reducing the number of digits, the octal and hexadecimal systems were introduced. You saw that the octal code required 3 binary bits for each octal character, and the hexadecimal system required 4 binary bits for each character. Even though number-based conversion was made easy through the use of binary-derived number bases, the human operator still works best with the decimal numbering system. For this reason, the best solution to this problem is the use of binary-coded decimal numbers, or BCD for short. Most binary-coded decimal numbers use 4 bits to express a decimal digit. As you saw earlier in the hexadecimal notation system, 4 bits can represent the decimal digits 0 through 9 and letters A through F. However, in the BCD system, the 4-bit digit groups for 10 through 15 are not used. For example, to code the decimal number 13 using the BCD code, the digits 1 and 3 are coded separately. Thus, 13 becomes 0001 in one group and 0011 in the least significant bit group. There are a wide variety of binary-coded decimal systems, but the most widely used of these systems is the 8421 BCD code. The 8421 BCD code is a weighted code in which the weights are 8, 4, 2, and 1. This code is a naturally weighted code because the weights are increasing in powers of the base 2. When encoding decimal numbers into the 8421 BCD code system, it requires as many groups of 4 bits as there are decimal digits. When converting decimal numbers into the 8421 BCD code, you proceed exactly as you would in the hexadecimal system, remembering you do not use the values 10 through 15. We will now pause for a short review of the material just discussed. Digital circuits operate with the binary system due to its simplicity in having only 2 states of energy, on and off. To simplify the calculations of large binary numbers, 2 common notation groups of bits are used, octal and hexadecimal. The octal system uses a base of 8 and only utilizes digits 0 through 7. The hexadecimal system, on the other hand, uses a base of 16 and uses digits 0 through 9 and letters A through F. All decimal numbers may be converted into BCD, binary, octal, or hexadecimal, or vice versa. Binary coded decimal numbers use 4 binary bits to express decimal digits 0 through 9. Binary coded characters for numerical values between 10 and 15 are not used. The most widely used BCD code is the 8421 BCD code. This concludes review number 1. Now that you have a basic understanding of how some of the common coding systems work, we will proceed into more of the digital circuits you will encounter in today's digital systems. The first such circuits we shall examine are referred to as flip-flops. To this point in the You Can Do digital series, we have described 7 of the basic logic gates found in digital equipment. There were the AND, OR, NAND, NOR, exclusive OR and exclusive NOR, and the inverter. None of these logic gates contain a memory, in that after a signal has been processed by the gate, it is ready to be controlled by the next incoming pulse. In contrast, a memory element is capable of remembering its input, even if the input changes. The most basic memory element is the flip-flop. You will be introduced to various flip-flop circuits and their properties. We will begin our discussion with the RS storage flip-flop. The flip-flop is a digital circuit with 2 outputs. The signals at these outputs are usually opposite. In other words, if one output is high, then the other output will be low, or vice versa. The outputs are called Q and not Q. The not Q is represented with a bar across the top of the Q. The RS flip-flop also has inputs. There is always one set input and a reset input. These are designated with the S and R. To better understand the RS flip-flop, we will examine its equivalent circuit. As you can see, the basic RS flip-flop consists of 2 NOR gates which are cross-connected. To better understand how the flip-flop functions as a memory device, we will examine this simple circuit. When both inputs are low, the outputs for Q and not Q could either be high or low depending on which gate turns on first. For example, let's assume that gate A turns on first. Since this is a NOR gate, it will produce a high output. This high is then fed into the second input of gate B. When gate B receives a high and low input, it will produce a low output. Now let's assume that gate B turns on first. When gate B turns on, it produces a high output, which is then fed into the second half of gate A. This causes gate A to output a low. This low output from gate A and the low from the set input will cause the not Q output to maintain a high state of energy. Next, we will see what happens when the reset input is low and the set input is high. The truth table shows that when the reset is low and the set is high, output Q will be high and output not Q will be low. To understand how this happens, you must first know and understand the truth table for the NOR gate. Basically, any high input will cause a low at the output, and when both inputs are low, then the output will be high. Since the set input of the flip-flop is high, then we know the output of this gate will be low. This low is then fed into the second input of gate A. Gate A now has 2 low inputs, which is the requirement for a high output. Therefore, the output of gate A will become high. At this time, gate B has 2 high inputs, which causes it to maintain a low at output not Q. And gate A has 2 low inputs, which causes it to maintain a high at output Q. This time we have made the reset high and the set low. As you can see from the function table, Q will be low and not Q will be high. Since the reset is high, we know that the output from gate A must be low. This low is then fed into the second half of gate B. Gate B now has 2 low inputs, one from the set input and one from the output of gate A. This forces the output of gate B high, As you will notice, the output at not Q is latched at high, and the output at Q is latched low. Here we have changed the inputs so that both the set and reset are high. The truth table shows that under this condition, both outputs Q and not Q will be low. This is easy to understand since we know that a high at any input of a NOR gate will cause the output of the gate to go low. The set input of a flip-flop is sometimes called the preset input, and the reset input is sometimes called the clear input. Next, we will examine the D flip-flop. The D stands for data. If you will look closely, you will see this flip-flop has two additional inputs. One is labeled D and the other is labeled C. D is for data input and C is for clock input. You will find, however, that some D flip-flops will not have the set and preset inputs. They were mentioned so you know they are available. To better understand the D flip-flop, we will examine its equivalent circuit. Notice that this circuit consists of two NAND gates, two NOR gates, and one inverter. We also have a clock input, a data input, and two outputs, Q and not Q. The clock input is a recurring signal that initiates the transitions of the flip-flop. When the data input is high and the clock input swings high, it places two highs at the input of NAND gate A and a high and a low at the inputs of NAND gate B. Notice the high was switched by the inverter at the input of gate B. Since gate A is a NAND gate and it has two highs at its inputs, we know that it will produce a low at its output. Also, since gate B is a NAND gate and it is receiving a high and a low, it will produce a high at its output. As you might recall, when a NOR gate has any of its inputs high, it will produce a low output. Therefore, NOR gate D will produce a low output, which is fed into not Q and into the second input of NOR gate C. At this point, NOR gate C has a low being applied at both of its inputs. Therefore, this NOR gate will produce a high at its output. Notice that the information which was present at the data input has now been switched to the Q output. Now suppose we make the data input low and apply the high clock signal. As you can see, gate A has a high and low signal being applied, and gate B has two high signals being applied at its inputs. The low and high condition of gate A will cause it to produce a high output. Gate B, on the other hand, now has two highs being applied at its inputs. This causes this gate to produce a low output. The high signal from gate A is fed into gate C. This high signal at gate C will cause it to produce a low output. The low output from gate C is applied at the Q output of the flip-flop and the second input of gate D. The low signal from gate B is fed directly into one input of gate D. Since gate D now has two low inputs, it will produce a high output. Therefore, output not Q will become high. By now you should have noticed that the output at Q will be the same at the data input when the clock signal is applied. As we mentioned earlier, some D flip-flops also have set and reset inputs. However, on most flip-flops, the two inputs are labeled preset for set and clear for reset. When the preset and clear inputs are at logic 0, they have no influence on the operation of the flip-flop. However, when the preset is made a logic 1 and the clear input is at logic 0, the flip-flop will set to its 1 or high state regardless of the control inputs and the clock. In the same respect, when the clear input is at logic 1 and the preset is at logic 0, the flip-flop will set to its 0 or low state regardless of the inputs at the data and clock. If, on the other hand, both of the preset and clear inputs are made high simultaneously, the output will result in an undetermined state. It could be high or low. Here we see a quad-type D flip-flop. This IC can be connected as shift registers or counter elements, as well as for specialized switching and timing control circuits. Even though this IC contains only 4 flip-flops with a common clock and reset inputs, there are other ICs available which will contain up to 16 flip-flops. As was just mentioned, the 4D flip-flops are controlled by a common clock and reset signal. You may also have noticed that the data inputs D0 through D3 to each flip-flop, as well as the outputs for Q and not Q, are buffered by separate amplifiers. Only during the time that the clock signal swings positive will the data which is present at the D inputs be transferred to the Q outputs. The reset function, however, is possible at any time and is independent of the clock signal. In the Type D flip-flop circuit shown thus far, the data input was not allowed to change while the clock input was high. This ensured that the flip-flop was left in a definite state after each clock pulse ended. If the input information changed while the clock pulse was high, the output at Q would change correspondingly. This would cause no problem so long as the flip-flop was used only for the storage of digital information. However, the flip-flop is used for other applications where this change of state could create false information. In such applications as counters and shift registers, the change of state at the output must be delayed until the inputs are no longer sensitive to change. One way to delay the changes in the output state until the clock pulse becomes 0 is by the use of the master-slave flip-flops. Here we see a simple master-slave RS flip-flop. It contains 2 clocked RS flip-flops and a logic inverter. The master-slave flip-flop will be contained in a single IC package. The operation of the master-slave flip-flop is very simple. For example, we will assume that the master flip-flop had previously stored a high at Q when the clock input is 0 or low. The clock input on the master flip-flop will be low and the clock input on the slave flip-flop will be high. This is due to the inverter in the circuit. This causes the output state of the master flip-flop to be forced into the inputs of the slave flip-flop. When the clock input becomes high, or 1, then the clock input on the master flip-flop will become high, and the clock input on the slave input will become low. This causes the inputs on the slave flip-flop to become ineffective. Therefore, the slave flip-flop will store its previous information, even if the master flip-flop changes its state more than once while the clock input is high. As you can see, the master-slave flip-flop is very effective in maintaining its information from one clock pulse to the next. Master-slave flip-flops are available in all flip-flop configurations. In the various flip-flops shown thus far, the control inputs are effective during the interval that starts at the leading edge of each clock pulse and ends at the trailing edge of the clock pulse. However, there are times when the inputs must only be effective for a short interval of the clock pulse duration. In such a situation, the edge-triggered flip-flop satisfies this need. In the positive edge-triggered flip-flop, the control input is sensitive for a short interval of time near the positive going transition of the clock pulse. The outputs of the flip-flop change shortly after this interval. In the negative edge-triggered flip-flop, the control input is sensitive for a short period of time near the negative going transition of the clock pulse. As before, the outputs of the flip-flop change shortly after this interval of time. Note that the symbol for the negative edge-triggered flip-flop shows an inverter operation at the input of the clock signal. Here we see the JK flip-flop. It is the most versatile of the flip-flop configurations. Notice that the JK flip-flop has 5 inputs. These are the J, K, preset, clear, and clock. The preset and clear inputs perform the same function as the set and reset inputs of the flip-flops previously discussed, except these inputs operate with the clock pulse held low. Notice the inverters placed on the IC. Also notice that a function table is given with the flip-flop symbol. Let's take a moment to examine this function table. When both inputs J and K are low, the flip-flop will remember its present state and the outputs will not change with the next clock pulse. Now suppose input J remains low and input K swings high. The flip-flop is then instructed to reset output Q to a low state on the next clock pulse and set not Q to a high. If, on the other hand, input J is made high and input K is made low, the flip-flop is instructed to set output Q high and output not Q low. And if both J and K have a high input, the output will toggle from one state to the next with each clock pulse. JK flip-flops may be found in digital circuits used for control, as registers, or as a toggle function. JK flip-flops are also available in edge-triggered devices. Notice that the negative edge-triggered JK flip-flop has an inverter at the clock input. We will pause for a short review of the material just discussed. The flip-flop is a digital circuit with two outputs which are labeled Q and not Q. The outputs of the flip-flop are usually opposite. In this video, you have examined the RS, D, master-slave, edge-triggered, and JK flip-flops. Master-slave flip-flops are used to latch an output to one state or the other while the clock pulse is high. Edge-triggered flip-flops are used when the inputs must only be sensitive during a small portion of the clock signal. Both positive edge-triggered and negative edge-triggered flip-flops are available. The JK flip-flop is the most versatile of the flip-flop configurations. Its uniqueness is in its ability to toggle from one state to the other when both inputs are high. This concludes review number 2. Now we will examine various counter circuits used in digital equipment. Because of their versatility, counters are used in many applications, such as arithmetic circuits, code converters, analog to digital converters, and waveform generators. This part of the video will concentrate on basic counter circuits. The primary function of all counter divider circuits is performed by the flip-flop, which, as you have seen, changes state when the clock pulse does a positive or negative going transition. We will begin our study of counter circuits with the basic ripple counter like the one being shown to you now. When a square wave signal is supplied to input A of the first flip-flop, it will produce a high at its output Q1. This high at output Q1 is then fed into the input of the second flip-flop. The output at Q1 is also used to drive other digital circuits, which will be discussed later. Notice that the duration of Q1's output lasts for one complete on-off sequence of the clock pulse at input A. Since the input of the second flip-flop stage is controlled by the output of the first stage, it will also go to a high state. Notice that the output of flip-flop 2 will remain high for one complete on-off sequence of flip-flop 1. Also notice the duration of the output on flip-flop 2 is 2 complete clock pulses. Next, the high output of flip-flop 3 is fed into the input of flip-flop 4. As you can see on the waveform, the output of flip-flop 3 will remain on for one complete on-off sequence of flip-flop 2. Therefore, the output at Q4 will remain on for 4 complete clock pulses. And finally, since flip-flop 4 is controlled by flip-flop 3, it will also produce a high output. The duration of this high output will be for one complete on-off sequence of flip-flop 3. Therefore, flip-flop 4 will stay on for 8 complete clock pulses. Since the flip-flop only has 2 states of energy, either on or off, it produces a binary count. The first flip-flop stores up to 2 counts, the second stage stores up to 4 counts, the third stage up to 8 counts, and the fourth stage up to 16 counts. Since this counter starts at 0 and counts up to 15, it is called a binary up counter. The simple ripple counter just described is called an asynchronous counter because one stage triggers the next. There are, however, disadvantages to this type of counter. One, the ripple counter has a much slower operation than do individual flip-flops. And two, the inability of the outputs to switch at precisely the same instant due to the propagation delay of each flip-flop stage. All logic devices will contain some propagation delay, and this becomes a problem when the stages are wired in series because the delay times are cumulative, in that the delay time of each stage in the series design will add to the total circuit delay. This problem is overcome by the use of synchronous or parallel counters. When wired in the synchronous configuration, all flip-flops are triggered at the same instant. Here we see a logic diagram of a synchronous counter. These counters are available in a wide variety of sizes and with a number of standard output decoders. As you can see, each flip-flop is controlled by the clock signal. Whatever data is entered must be entered with each clock pulse, because only when the clock enables each flip-flop can the counting or dividing operation take place. Notice that all the outputs, Q1, Q2, Q3, and Q4, have the same symmetrical pulse shape. Each output pulse will be the width of one complete square wave cycle of the clock pulse input. Also note that each output occurs one complete clock cycle after the previous one. The reset signal can be enabled at any time and is generally kept at logic 0 after the start. Also, as long as the clock inhibit signal is at 0, the counter will advance one count during each positive clock pulse transition. Since the synchronous counter does not have nearly the propagation delay of an asynchronous counter, it is better suited for high-speed operation. However, some delay does still exist, and the actual operating speed is somewhat less than the maximum theoretical speed. This is due to the fact that since the clock must drive all the flip-flops simultaneously, it requires more power from the clock circuit. When the clock is heavily loaded with flip-flops, the propagation delay is increased and the counter speed is reduced. Despite this limitation, the synchronous counter circuits are still superior to the asynchronous counter. Oftentimes, counter circuits are designed to perform a specific task. One such application would be in the division of a given clock signal by a pre-selected value. This function is easily performed by a programmable counter. Programmable counters are used in frequency synthesizers, phase-locked loops, and other applications which require frequency division. A variety of programmable counters are available on today's market. By presetting the stages of a counter, you can design a circuit that in some cases will count either up or down because each separate stage can be made to reset when the preset count has been reached. Here we see a typical programmable divide by n counter. Notice the inputs labeled P1, P2, P3, and P4. These are the counter inputs which can be programmed to allow the user to determine the desired division of the input clock frequency. Also notice the input labeled PE. This is the programmable enable input. This allows the counter to divide by the pre-selected value at the inputs of P1 through P4. Next is the input terminal, labeled CF for carry forward. This input is used for cascading the counter when a higher value is needed than that which can be achieved from a single stage. The terminal labeled 0 is also used when cascading stages together. CF is the input and 0 is the output. The clock inhibit input allows the pulse counting function to be disabled. The reset, clock, and outputs Q1 through Q4 perform similar functions as have already been described in the previous counter circuits. Now that you know what the input and output functions are, let's examine this circuit to see how it works. We will start by programming inputs P1 through P4 with the binary number 9. P1 will have a binary weight of 1, P2's binary weight is 2, P3's binary weight is 4, and P4's binary weight is 8. So the input signal placed on the P1 through P4 will be 1, 0, 0, 1, respectively. When the programmable enable input is momentarily taken high, the internal preset logic is enabled. This allows the number appearing on inputs P1 through P4 to be loaded into the counter and appear at outputs Q1 through Q4, once the desired number has been preset. The counter will begin counting down from the preset number. It will do this on the first positive transition of the clock signal. The counter will continue to count down on every positive transition of the clock signal. For the first 9 pulses, output 0 will remain low because the count has not yet reached 0. On the 10th transition, the counter goes to 0, 0, 0, 0 at outputs Q1 through Q4, and output 0 will go high. As you can see from the illustration, the clock pulse was divided by 10. For every 10 clock pulses, output 0 would go high once. Now let's see how a programmable counter would work in a typical application. Here we see a simple block diagram of a digital clock. The first block in this system is a 40 kilohertz oscillator. It will produce a series of 25 microsecond pulses into the first programmable counter. As you notice, the first counter is a divide by 40,000 counter. In other words, for every 40,000 clock pulses, this circuit will produce 1 output pulse. These pulses will occur at a rate of 1 each second. The 1-second pulses are then fed into a divide by 60 programmable counter. This counter has 2 outputs, one of which is used to drive a binary to 7 segment decoder driver circuit, which further drives a 7-segment display. This part of the system is used to show the seconds on the clock. The other input is fed into another divide by 60 programmable counter circuit. This circuit also feeds a binary to 7 segment decoder driver circuit and 7-segment display. This part of the circuit is used to show the minutes on the clock. The second output from the divide by 60 counter is fed into a divide by 12 counter, which is used to show the hours. An actual clock circuit of this nature would be a little more complex than the one being illustrated, but the operating principle will remain the same. So far, you have seen how flip-flops may be connected to count from 0 to the modulus number, or from the modulus number to 0. The modulus is an integer which designates the number of states through which a counter sequences during each cycle. But what happens if there are 2 numbers to be combined within the system? After all, this is what the computer does best. This simple combining of numbers is performed by circuits referred to as adders. As you shall see, there are 2 basic adder circuits. These are the half adder and the full adder. The basic adder stage will accept 2 inputs and generate a sum output as well as a carry output. The half adder, which is much simpler than the full adder, will only accept binary numbers to be added in a single bit form, and it will not accept a carry-in from a previous stage. Therefore, this type of circuit is generally used as the least significant stage of a full adder design. To better understand how the half adder stage works, we will examine its equivalent circuit. Also shown is the truth table for this circuit. Notice that this circuit consists of 2 inputs, A and B. This circuit also has 2 AND gates with an inverter at one of their inputs. These 2 AND gates are then fed into an OR gate, which produces a sum output of the 2 input bits. There is also a third AND gate, which does not have an inverter at its input. This gate is used to produce the carry-out bit of the stage. From the truth table, we see that the sum is 0 and the carry is 0 when both inputs A and B are 0. We also see that a sum is 1 with a carry of 0 when input A is low and input B is high. On the other hand, when input A is high and input B is low, the sum will be 1 with a carry of 0. And when both inputs A and B are high, the sum will be a 0 with a carry of 1. The full adder is distinguished from the half adder in that it can accept a carry-in input. Since the full adder can add 3 bits, input A, input B, and carry-in, it will have a decimal output of 0, 1, 2, or 3 in binary, if both the sum and carry-out bits are considered together. Here we see the equivalent circuit for a full adder stage. Also shown is the truth table. Notice that the full adder circuit has 3 inputs, A and B, and carry-in. This circuit also has 2 outputs, which are labeled sum out and carry out. As you can see, this circuit consists of 2 exclusive OR gates, 2 AND gates, and 1 OR gate. We will now examine this circuit to see how it works. As you can see from the truth table, when all 3 inputs, A, B, and carry-in are low, the sum and the carry-out outputs will also be low. Now suppose that inputs A and B are kept low and the carry-in input is brought to high. This causes the sum output to go high while the carry-out output will remain low. Next, we have made input A low, input B high, and the carry-in low. This also results in the sum being high and the carry-out remaining low. This time we have input A low and input B high, and we have placed a high at the carry-in input. This causes the sum output to go low and the carry-out output to go high. Now we have made input A high and placed a low at inputs B and carry-in. As you can see, the sum output will go high and the carry-out output will swing low. Next, we have left input A high and input B low, and we have placed a high at the carry-in input. This causes the sum output to go low and the carry-out output to swing high. Now suppose we make both inputs A and B high while leaving the carry-in input low. As you can see, this causes the sum output to remain low and the carry-out output to remain high. When all 3 inputs are made high, the sum output and the carry-out output will also be forced high. The single-bit adders we have just discussed would not be very useful in a computer system. However, by cascading a number of the single-bit adders together, we can create a circuit that will add a group of binary numbers. Here we see a simple 4-bit ripple adder circuit. As you may have already noticed, the stages are all full adder devices with a carry-in and a carry-out. Inputs A0, A1, A2, and A3 will form one of the 4-bit numbers. And inputs B0, B1, B2, and B3 will form the other 4-bit number. Let's see how this simple circuit works by adding binary 9 to binary 5. We will make inputs A0, A1, A2, and A3 the binary 9 input. Since the number 1 full adder is the least significant bit, its binary weight will be 1. And since the number 4 full adder is the most significant bit, its binary weight will be 8. Remember, binary numbers double in magnitude as they increase. Inputs B0, B1, B2, and B3 will represent the binary 5 input. Therefore, the B inputs on full adder stages 1 and 3 will become high. Now we will examine one stage at a time to calculate the binary output of this circuit. We will begin with the first full adder stage. The first full adder stage has a high on inputs A0 and B0 with a low at the carry-in. Therefore, the sum of this stage will be 0 and the carry-out will be high. The second full adder stage has a low on inputs A1 and B1 with a high at the carry-in input. This causes this stage to produce a high at the sum output and a low at the carry-out output. The third full adder stage has a low at input A2 and a high at input B2 and a low at the carry-in input. This results in a high at the sum of the third full adder and a low on the carry-out output. The fourth and final full adder stage has a high on input A3, a low on input B3, and a low at the carry-in input. This causes the sum of the fourth stage to swing high, and the carryout will remain low. When we add the binary bits together, we see that we have acquired the sum of 14, which is the correct answer to 9 plus 5. Since the ripple time is the limiting delay in the 4-bit ripple adder circuit, a carry look-ahead circuit is usually included in the circuit design to minimize this delay. A typical propagation delay from carry input to carry output is 12 nanoseconds. Therefore, this style adder circuit would have a propagation delay of approximately 48 nanoseconds. We will now pause for a short review of the most recently discussed material. The three counter circuits we discussed were asynchronous, synchronous, and programmable. The most common asynchronous counter is the ripple counter. As you observed, the clocking input was derived from the previous stage output. The operational speed of this counter circuit depends only on the signal propagation through the network. The synchronous counter differs from the ripple counter in that the counting operation is controlled by clock pulses from a master clock. This results in the counting operations maintaining a constant time interval between successive transitions. The programmable counter, on the other hand, is capable of being programmed so it can count to any number from 0 to its maximum modulus. You have also seen how two different types of adder circuits work, the half adder and the full adder. The basic adder stage will accept two inputs and generate two outputs. The two outputs are the sum and the carryout. The half adder will only accept single binary bits to be added. These bits are placed on inputs A and or B. The half adder is generally used as the least significant stage of a full adder network. The full adder, on the other hand, will also accept a carry-in bit as well as the two inputs on A and B. By cascading full adder stages together, we can create a network that will add a group of binary numbers. This concludes review number 3. Next, you will learn a shorthand method for writing logical statements. In 1847, a famous English mathematician and logician by the name of George Boole created a system of mathematical logic whereby complicated combinations of logical statements could be easily expressed. This system was named Boolean algebra in his honor. As you will see, Boolean algebra provides a ready-made method for digital designers to handle the logical statements that are involved in every binary digital system. The three most basic operations in Boolean algebra are called the AND, OR, and NOT. Even though Boole's system included many other operations, these three are the only ones needed to add, subtract, multiply, and divide. As you can see, the AND may be represented by either the times sign or the period. The period is more often used than is the times sign. The OR is represented by the plus character, and the NOT is represented by the bar. We will now review the 5 basic gates to see how they will be expressed in Boolean algebra. Here we see the AND gate and the truth table for the AND gate. Also shown is a table with the Boolean equations for each function of the AND gate circuit. In the first function of the truth table, both inputs A and B are low. This produces a low at output C. In Boolean algebra, this is stated as not A and not B equals not C. Remember, the period represents and the bar represents not. In the next function of the truth table, input A is low, input B is high, and output C is low. In Boolean terms, this is written as not A and B equal not C. The third function of the truth table shows a high at input A, a low at input B, and a low at output C. In the Boolean system, this is stated as A and not B equals not C. The last function of the truth table shows a high on both A and B will result in a high output at C. In Boolean terms, this is stated as A and B equals C. Now we will examine the OR gate. It is also shown with a truth table and a Boolean table. As you can see in the first function of the OR gate truth table, a low at inputs A and B will produce a low at output C. This is expressed as not A or not B equals not C. Remember, the plus sign indicates an OR function. Next, the truth table shows a low on A and a high on B and a high at output C. Using the Boolean system, this is stated as not A or B equals C. The third function of the truth table shows a high on A, a low on B, and a high at output C. Using the Boolean system, this is stated as A or not B equals C. And the last function on the truth table for the OR gate shows that a high on input A and a high on input B will result in a high at output C. In Boolean terms, this is expressed as A or B equals C. Here we see the inverter, or NOT gate as it is sometimes called, with its truth table and Boolean table. As you can see from the truth table, when input A is high, output B will be low. This is easily expressed as A equals not B. And when we reverse the input and make A low, output B becomes high. In Boolean, this becomes not A equals B. Now let's examine the NAND gate. Remember, the NAND gate is a combination of the AND gate and an inverter placed at the output. As you will notice from the truth table, when A is low and B is low, the output at C will be high. In Boolean, this is expressed as not A and not B equals C. Next, we see that a low on A and a high on B will produce a high at output C. In Boolean, this is easily expressed as not A and B equals C. When input A is made high and input B is made low, the output remains high. Boolean terms say A and not B equals C. And when both inputs A and B are high, the output will swing low. This is expressed as A and B equals not C. The final gate we shall examine is the NOR gate. As you recall, the NOR gate is a combination of an OR gate and an inverter placed at the output. From the truth table, we see that when inputs A and B are both low, output C will be high. Boolean terms express this as not A or not B equals C. We can also see that when A is low and B is high, output C will be low. In Boolean, this is not A or B equals not C. And when input A is high and input B is low, output C will remain low. You can readily see in Boolean this is A or not B equals not C. And finally, when A is high and B is high, then output C will be low. This is expressed as A or B equals not C. We have covered many subjects in this video, which a good technician must know and understand. Therefore, it is recommended that you view this video many times to gain a full understanding of the material being presented to you. You-Can-Do videos are not only designed to make learning electronics fun and easy, but they are also designed to give you confidence in your own technical knowledge. This confidence will show as you competently repair today's solid-state equipment.